Hi and welcome back to Module 8, and today we are looking at video number 8, Carbon-13 NMR. So we looked in our last video at the proton NMR, and we found that it was quite complex and a few different things that we need to remember, such as splitting patterns and the intensity of the peak and so forth, to be able to help us determine what is in our sample or our unknown solution, and using that with a combination of other analytical techniques, we can use that to work out what our sample might in fact be. One of the other things that we also use, which lines up with our previous outcome, is also using NMR, and in this case carbon-13 NMR. Now, we've already talked about how do we choose the hydrogen NMR and the carbon-13 NMR, and we've talked about the spin on the nucleus. Well, obviously that still applies with carbon-13 NMR, but carbon-13 NMR is a little bit simpler. So let's have a look at it. So with our carbon-13 NMR spectrum, we use that isotope. If we think about carbon-12, carbon-12 is the most abundant. Carbon-13 is only about 1% in abundance. So it's not that common that we have, and so it's going to take a long time to produce the spectra that we're going to have, because it's not a lot of it there. It's going to take some time to generate that spectra, and it's not going to provide us the detail that the proton NMR does. But using this isotope can give us information about the molecules in the sample that contain the carbon atoms. But the height of the peak is of no use to us, unlike in the hydrogen. Every carbon environment, and we've talked about the chemical environment already in a previous video about the chemical environment of the hydrogens and the carbons, so that's obviously still relevant here. Each carbon environment is represented by a single peak, and the type of carbon that we have will be indicated by the chemical shift that we're going to see. Now, looking here on this table, and again I'll move me out of the way, looking over here on this table, this is what you're provided with in your data sheet that you will get in the exam. So this is something that you don't need to learn off by heart, but certainly how to apply it. We can see a signal. We'll see a peak on our NMR, but the peak that we see and where it is located will tell us how shielded or deshielded the carbon's nucleus is, again by the electrons around the outside, based on how far away it moves from the TMS signal. And remember, the TMS signal is on both the proton and the carbon NMR, and it's our benchmark. So looking over here, if we're looking at the type of carbon here, you can see it's a carbon-to-carbon bond, which is going to be your alkanes. We're looking here 5 to 40, we're going to see something there. Now, if we've got a halo alkane, you can see the hydrocarbon on this end connected to a carbon, and we've got our chlorine or bromine on the side. We should be seeing a peak then around the region of between 10 and 70. In the next one here, obviously we've got our ketones, so around the 20 to 50. Again, our amides, 25 to 60. Our alcohols, esters, will be in that range. You can obviously see these are alkenes, 90 to 150, and so on. So that's going to give us an idea of what the carbon environment is. Use that in conjunction with our hydrogen environment, and then we're going to be able to get a bigger picture of what the compound or the sample, organic sample, might be. Then, if we use our infrared, it helps to support our argument, and our mass spectrum, again, even further helps with support, because it will give us our mass of that compound, and that's all the evidence that we're going to use to justify why the compound might be the compound you say it is. So looking here, if we have a look at this spectra, again, this is one we've looked at previously on the hydrogen environments. You can see here we've got our TMS just down this end, and then we have got two peaks. So those two peaks are telling us straight away that there are two different environments that we're going to be seeing here. So one peak's around the 18 and one peak around 37. So if we look back at our previous table, and I mean, obviously we've got our formula here, and that certainly helps, but you're not going to always have that. But in our learning stages, it's certainly useful to help us determine. You can see this carbon here is connected to another carbon, and here we've got 3 different hydrogens off it. This carbon is connected to another carbon, but we've got a chlorine and a couple of hydrogens off. So this environment of the carbon is different to this environment of the carbon. Now our peak at around that 18 mark is going to be our carbon to carbon chain that we can see in this previous one up here in the range of the 5 to 40. But then we look at the next one, and the next peak is at around that 37. Now if we go back here and have a look, you'll see that there is some overlap. So 5 to 40 could be the range of that C to C, but you're also looking here and going 10 to 70 is where our halogen is as well. So in this case, this will be our C to Cl bond that we're seeing just here. So having a look at this one's out of Pearson. And again, I'll just pop me over here. The carbon-13 NMR spectrum of an alcohol has the molecular formula of C3H8O, and it's shown below. Determine the structure, so we want you to draw it, and the identity. So we've got some clues obviously here. So let's have a look and see what we've got. Again, we've got the TMS signal, that's our benchmark, and we now have 2 different peaks. So we've got one at about 25, and we've got another peak at around 64-ish. So, looking at our formula, you can see C3. We know it's an alcohol. So C3, we're looking at a propanol. Now, when we're looking at a propanol, remember there are isomers. So the alcohol is not always on the outside there. So you need to use this information carefully. So we do know it's an alcohol. And the peak at 25 is again that the C to C bond, which is about our CH3 group, CH3 going to the C in the center. So that's our carbon to carbon bond. Our peak at 64 is our hydroxyl group there. So we're going to know that it's going to form either propan-1-ol or propan-2-ol. How do we know which one it is? First thing I would do is draw the structures of both. Now looking in this picture here, we've got 2 chemical environments. So looking at the 2 structures you have drawn for propan-1-ol and propan-2-ol, which one has 2 chemical environments? So yes, there are 3 carbons, but only 2 peaks. So 2 of those carbon environments must be the same. Have a pause, try and work it out for yourself. Once you've got an answer, press play and check and see if you're right. Okay, well I hope you did stop the recording and check your answers. Now, looking here, our answer is in fact propan-2-ol. So our hydroxyl group is on the middle carbon. And that way then we've got the CH3 and the CH3 environment on either side, connected in the center to a carbon with a hydroxyl group on it. Hopefully you got that one right. Have a go at this one. The carbon-13 NMR spectrum of an alcohol, so similar kind of question, that has the molecular formula C4H10O is shown below. Again, we have got 2 peaks here. So have a look at where the peaks are. Don't forget all the isomers. So while yes, C4, we can look at the bute family, but also don't forget there are a range of different isomers that we can get. Draw them all out and then use the peaks, the number of different carbon environments, to help you with the answer. Come to class with that and we'll see how you go. See you then.